Okay, so part 3 of this final exam solution video. So this is wanting you to match items, match things up. Okay, so let's look at A. Okay, whoa, let's see here. Okay, so it looks like the way that this is structured is that like this is like a bank of things, and then I'm going to write those things over here. Okay, so delta x, that would be the width of the rectangle. So it looks like that is C on my picture right here, is that width of the rectangles, okay? F of x3 multiplied by delta x. So f of x3 would be this height here, and if I multiply that by delta x, then that would give me this area. So that is A3. Okay. And then f of x3, that would be the height, that would be this distance here, which is the height at x3. So that is B in the graph. The sum from 1 to n of the f of xi times delta x, that would be the sum of each of these areas added up. So this is going to be a1 plus dot 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 plus an. And then the limit as n goes to infinity of that sum is going to be the entire integral. So if I let the number of rectangles go to infinity, those rectangles are going to get skinnier and skinnier, and it will give us the actual integral. Okay. Next, a child walks at a constant rate of 3 feet per second and lets go of a helium balloon while walking. The balloon rises vertically at a rate of 4 feet per second. So we have a child walking, and we have a balloon is going to be rising here. And so this is where the child let go of the balloon, and then the child is over here now. So we'll put C there for child, or we'll, I don't know, we can call this distance x. So x is the distance from where the child let go of the balloon to where the child is now. So maybe I'll draw a child here. There's my child. Okay, and then this is the balloon up here. And the height of the balloon, I'm just going to call it h. Okay, and so the question is, I want to say, let's look at what I'm given here. So I'm given a rate of change here of 3 feet per second, and that is the rate at which the child is walking. So that is my dx dt is 3 feet per second. And then dh dt is also given, and that is the balloon rises vertically at a rate of 4 feet per second. So that is equal to 4 feet per second. And then it asks, at what rate is the distance between the child and the balloon changing? So that's this distance, which I'm going to call, I guess I'll call it y. And so I want to find dy dt, right? And so what that means is that I need to get a relationship between y, h, and x, and then I want to take the derivative of that equation with respect to t so that these rates of change are going to show up. So I can look over here at my picture, and I can see how x, h, and y are related to one another, and I can just use the Pythagorean theorem. So x squared plus h squared equals y squared. And so then I can take the derivative of this implicitly with respect to t. So I get 2x dx dt plus 2h dh dt equals 2y dy dt. And then the question is, I want to find the rate, the distance is changing 10 seconds after the child let go of the balloon. So after 10 seconds, we are going to have that x is going to be equal to, well, it's 3 feet per second for 10 seconds, so 30 feet. Y is going to be equal to Well, it's rising at a rate of 4 feet per second for 10 seconds, so that's 40 feet. Oh, sorry, that is h, excuse me. Maybe I should have called it, well, anyway, I called it h. And then y is going to be that distance. So y is going to be the square root of 30 squared plus 40 squared, which is going to be, well, it's a 3, 4, 5 triangle, so it's going to end up being 50. But I could plug that into my calculator and see it. Okay, so 50 feet. So now I can plug all of these values in for what I know. So I'll have 2 times 30 times 3 plus 2 times 40 times 4 equals 2 times 50 dy dt. And then I can solve that for dy dt. And I'm going to get dy dt equals, so if I simplify all of that, I'm going to get 100 dy dt equals 500. I divide it over, I get dy dt equals 5 feet per second. All right, the next one, I have a box of the volume 100 cubic inches. With a square bottom and top is constructed out of 2 different materials. All 6 sides will be constructed. The cost of the bottom is 4 cents per inch, and the cost per square inch, and the cost of the top is 1 cent per square inch. Okay. Write a formula for the surface area of the box as a function of a single variable. Okay, so I know that x squared h, which is the volume, is equal to 100. So that tells me h is equal to 100 over x squared. And so the surface area of the box is going to be S equals, well, it's going to be 2 of the top and bottom are the same, so 2x squared, plus, and then I have 4 of those sides, so 4xh, which is equal to 2x squared plus 4x times 100 over x squared. So that's going to be 2x squared plus 400 over x. I do want to just mention that we should be a little bit leery of canceling out that x divided by x. But because, why? Sometimes when you cancel out an x divided by x, you lose solution. So anytime you're doing that, you should be a little bit cautious. But I note that there's an x left in the denominator, so still x equals 0 is not a solution. So dividing by x over x actually didn't make us lose solutions or anything in this case. But anytime you simplify x divided by x, you should be a slightly bit nervous about losing solutions or something. Okay, now write a formula for the cost of manufacturing the box as a function of a single variable. C of x should be equal to, well, the 2x squared is multiplied by, okay, so the bottom is 4 cents per square inch. So 4x squared plus the top is 1 cent per square inch. So 1x squared plus the sides are 1 cent per square inch. So it's going to be 400 over x times 1, which is just 400 over x. So that is what that is, okay? Then it says find the dimensions of the box that minimize the total cost. So C prime of x is going to be equal to, so that adds to 5x squared plus 400x the minus 1 is how I'm going to write that, because that'll help us with taking the derivative. So we're going to get 10x minus 400x to the minus 2, and I want to set that equal to 0. And so I can get a common denominator by multiplying this guy by x squared over x squared. And so that's going to give me 0 equals 10x cubed minus 400 over x squared. When I set that equal to 0, that's equivalent to setting the top equal to 0. So I'm going to get 400 equals 10x cubed, divide by 10, and x is equal to the cube root of 40, which is approximately 40 raised to the 1/3 power in my calculator, 3.4199. And the question is the dimensions of the box that minimize the total cost. So there is my approximation for x. Now h should be equal to 100 over x squared, which is 100 over the cube root of 40 squared, which is approximately 8.549. And then to justify that it is a minimum, I can just do C double prime and plug in that value of x and make sure that it is a minimum by ensuring that the function is concave down. Minimum, concave up. It needs to be concave up to be a minimum. So let's just check. So if I take the second derivative of this, I'm going to get 10 plus 800 x to the minus 3. And if I plug in 3.419 for x, I'm going to get that that is positive at x equal 3.149, and so it is a minimum. And so that is the part about justifying that it's a minimum. All right, the last one, I want to identify which of the following is the largest and which of the following is the smallest. So let's do all of this. Okay, so g prime at 1, that's going to be some positive numbers. I'm just going to write positive here, just so I can see it. I may have to compare it with something else later, but let's just identify which ones are positive and which ones are negative. The integral from 1 to 5 of g of x dx. So this is going to be some positive area. And if I want to approximate that area, I'm just going to approximate it as though it were like, a rectangle and a triangle, and I'm just going to get a rough idea of what this might be. This is about 4, and this is about 4 times 2, 1/2 times 4 times 2. So this would be about, so 4 times 2 is 8. That's about 4 also. So this is about approximately 8, and it's a positive number. This number is a slope, and if I do the rise over run of this, I'm just going to make it longer so I can kind of see. The rise over run of this is like up 1 over less than 1, so this is about 1, so close to 1, just to kind of give us an idea of what that might be. Okay, this is the a Riemann sum, going from starting at 1, so that's my starting point, and then I am going over 10 times 0.4, so I'm going over 1, and so that will be this Riemann sum. Now the first one is going to start taking it from the right hand side, so that's going to be a right hand Riemann sum with 10 rectangles. The very last one will happen at 1 plus 0.4 times 10. So 1 plus 0.4 times 10, that's going to be 5. So the very last one is taking a height at 5. So this is actually going to be a overestimate of the integral from 1 to 5 of g of x dx. Okay, and then g double prime at 1. So at 1, I want to do g double prime, so I can see that it's concave down. So this is actually a negative number. And so which one of these is the biggest? Which one of these is the smallest? The only one that's negative is g double prime of 1. Of 1 is going to be the smallest. And then the largest is going to be that Riemann sum. So that's going to be that overestimate. And so how do we know that it is an overestimate? Well, what I can do is I can go ahead. So you may be asking, well, how do you know it's a right-hand Riemann sum? Well, I'm just going to write out the first few terms. So if I plug in k equals 1, what do I get? I'm going to get g of 1.4 times 0.4. So I can see that the height is being measured on the right-hand side at 1.4 is where it's measuring the height of the rectangle. Plus, the next one is going to be g of, I'm going to add 0.4 again, so it's going to be 1.8 times 0.4. So I'm, again, taking the measurement of the height from the right-hand side of the interval. And when I get to the very last one, when k is 10, it's going to be taking the reading at 5. So 1 plus 0.4 times 10 is going to be 1 plus 4, which is 5. So this is actually a right-hand Riemann sum, and I can tell that just by plugging in values of k and see where they get me. So that is the end.